Okay, this topic is distinguishing solid, liquid, and gas phases of a pure substance. So this is getting us used to the idea of how we represent solids, liquids, and gases on the atomic level, like if we could actually see atoms. So this solid, what we're looking for is that the atoms or molecules making up a solid, so don't get put off if it's like just atoms or if it's molecules. We'll learn a little bit later about the differences between like ionic solids and molecular solids and stuff. But what you're looking for is that the basic units of the solid, whether that's atoms or molecules, they should be packed really close together. Okay, so it's the most dense form of the particular element or compound you're looking at. They should have some sort of regular order. Okay, so they'll be closely packed. Okay, with the exception of water. We'll come back to that now. I'm going to cycle back around to water. Okay, so they should be ordered, they should be dense. A liquid is going to be slightly less dense than the solid, but it's still going to be pretty well packed together. So less dense than a solid. So there'll be little gaps because the atoms or molecules of a liquid can kind of slide over each other. So they are disordered, okay? They will also flow within a container, but they're going to be subject to the laws of gravity. So they will sort of fill a container from the bottom up, okay? And they'll slosh around, right? So they are generally disordered, okay? A gas is extremely spread apart. So all the atoms, molecules are very as diffuse as they can be. So that is the least dense phase of matter. And again, it is disordered like a liquid, but just very, very spread out. So the exception to this is with water. So ice is less dense than water, okay? The reason for that is because ice in the solid state contains what's called hydrogen bonds, which you won't have learned about at this stage, but basically it's a different kind of bonding, and the way it holds the water molecules together in the solid structure, there's actually little gaps in it. So there's what kind of looks like pores or openings. So within a certain volume of H2O. For ice, it contains less hydrogen and oxygen atoms than it does in water, which is why ice floats on water. So this is a fairly easy one to remember. If you have a cold drink, you see the ice always floats to the top, unless it's got stuck to the bottom, right, with adhesion. Or like if you see a frozen lake, don't skate in a frozen lake, right, very, very dangerous. The ice is on the top, which is good if you're a fish, okay? So water is the weird one, that ice is less dense than water. That's to do with the hydrogen bonding and its solid structure. So the way I would approach these kind of problems is to actually kind of sketch out a kind of line and get the melting point and boiling point sort of squirreled away with what you understand by that. So the melting point is going to be the transition between the gas and the liquid phase. If you heat something up from a solid until you get to its melting point, what does it do? It melts. If you have a liquid and then you cool it down below its melting point, what does it do? It freezes, okay? And then at some higher temperature, you're going to have a boiling point. So above the boiling point, what happens once a liquid boils? Well, it turns into a gas or a vapor if you prefer. If you cool a gas down below its boiling point, it condenses back into a liquid, okay? So these are these two important temperatures to know. And you can kind of block off areas now where you know if that temperature is below the melting point, then your particular substance you're looking at is going to be a solid. It's going to be in the solid zone, right? If the compound or element that you're looking at is above the boiling point, it's going to be in the gas zone. If the temperature is in between the melting point and the boiling point, then it's going to be in the liquid zone. So for any compound element or whatever, just look at what the individual melting and boiling points are. Okay, so we've been given carbon monoxide. The melting point is -205. Okay, so you may not be used to the Celsius temperature scale, right? It's based on water, which has a melting point of 0 degrees Celsius and a boiling point of 100 degrees Celsius. And we know that there are temperatures colder than the temperature at which water freezes into ice. So we also have negative temperatures in Celsius, which go all the way down to minus 273.15, which is absolute zero, which is based on the third law of thermodynamics. That's a temperature at which atomic vibrations stop. You don't have to worry about that until Gen Chem 2, but that's where it comes from. So that is what the Kelvin temperature scale is. The size of a degree is the same in Kelvin as it is in Celsius. They just have a different starting point. But anyway, we're sticking to Celsius for now. So the melting point of carbon monoxide is minus 205, and the boiling point is minus 192, which doesn't sound like it, but it is warmer. Okay. I don't know why that changed color, but we're just going to go with it. Okay. So the temperature we're actually at in each of these pictures, let's try and sort of plot it on. Okay. So minus 203 degrees Celsius. Well, that would be about, let's get an arrow. Minus 203 would be about here, right? So minus 203 degrees Celsius would put us in the liquid zone right here. So we would be looking for a picture that kind of looks like a liquid. So it should be packed closely together. Carbon monoxide is going to be sort of two atoms. So it'll be two different colored atoms bonded together. So one will be like this, and the other one will be, let's just pick a color. I'm just picking random colors. So it's going to look a little bit something like this, and they should all be kind of close together, but jiggly. Okay, so that's what we're looking at for A. Okay, and then for B, minus 162, that is also going to be in that liquid zone. Okay, so that's going to be sort of closer to here, but still going to be, oh, colors are going crazy. What are we going to do? That is going to, I might as well double down and match it. Minus 162 Celsius. Okay. If all my buttons worked on my computer. So again, that's going to be between the melting and the boiling point. So that is going to be a liquid. So it's going to look the same. And then minus 209. Well, that is going to be really... Oh, hang on. I totally misread that. Oh my goodness. 162 is not going to be there. What are we doing? 162 is going to be... This is what happens when you talk. It's going to be here, right? Above minus 192. So let's put that in there. Minus 162 degrees Celsius. That's going to be a gas. So we're going to have the same molecules in the gas phase. So this is for B, right? But they are going to be spread apart more. So in the liquid phase, we'd be expecting them to be all kind of jumbly and like close together, like randomly organized like this, blah, 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 blah. Let's do another one over here. I don't know, close, jumbly, like so. Not exactly round, but you know, what are you going to do? So that would be for A, kind of jumbly. But then for the gas phase, they're going to be like spread apart. So you'll probably only see like maybe 3, maybe 4 molecules in the whole screen there. Like there'll be one over here, and then there'll be another one down here, something like that. So it'll just be really spread apart. And then minus 209, wherever my arrow's gone, is going to be, let's pick a different color. Why not? It's all gone crazy. It's going to be this side of the melting point line. Okay, so that will be solid at those temperatures. So minus 209. There we go. So something a little bit like this. So these should be all lined up in a very sort of close packed array. So, and it will look really regular. Okay, so you'll be looking at something a little bit more like, if I could change the color, one of those. And you know what, I'm just gonna do a few. It's gonna be quicker. They're gonna be all like packed together. I'm not sure exactly how, but we'll take a look in a second and see how close our predictions match. Now, I can't make the slider work on my view of these questions, so what we're gonna have to do is we're gonna have to just cheat and go look at the answers. Okay. There we go. So it's going to be something a little bit like this. So I'm going to be naughty and click onto the explanation so you can see what I mean with what these pictures look like. So you can see we're pretty accurate with our liquids just kind of jumbled up and disordered, but still fairly dense. Our gas, they are really far apart, and in our solid, they are closely packed together. Okay, so I want to show you one more thing on this kind of question, which is what the solid structure of water looks like. So for all these kind of questions, you're going to have similar thing with a liquid, solid, gas, depending on what the actual element or compound is, will depend on what the actual individual molecule looks like. Okay, but we do need to look at this whole thing of water with the solid state of water looking a little bit different. Ah, look at that. You were listening to me, Alex. So we'll look at the explanation. So for this case, 260, we'd expect this one to be a gas, so the particles should be far apart. And because remember, the melting point of water is 0 and the boiling point is 100. For this -25, we'd expect to be seeing a solid, and for 12, we'd expect to see a liquid. So let's contrast B and C for the solid and liquid phases of water, which is going to be down here somewhere. So I'm going to just get rid of these guys because they're going to be in the way. Sorry, beautiful drawing. Off you go. Right. Scroll down, scroll down. So gas looks the same, right? But look at the solid form of water. Look at these gaps in it. So the way you can spot it is it's still a nice regular array of water. You just kind of have to learn and recognize that water is actually slightly less dense in the solid phase than it is, and this is the liquid phase of water. So you can spot that because of the disorder. But actually the water in the liquid phase is slightly more dense, which is why ice floats on water. Okay, so I think that's everything you need to know about those kind of questions.